Ever since high school calculus, there's been one derivative that's always bugged me: the absolute value of x. Sure, you could define its derivative as a piecewise function, but to me, that felt like taking the easy way out, and I wasn't ever really satisfied with that answer. But what if you could find the absolute value of x's derivative through actual differentiation? The problem is the absolute value function itself. I mean, it's easy to define it as the distance a value is from 0, or as negative x when x is less than 0, and x when x is greater than or equal to 0. But that's just another conditional definition. What we need is a way to define the absolute value of x as a non-piecewise function using functions we know how to take the derivative of. An important property worth noting is since the absolute value function measures distance from 0, it always outputs a positive number. So, whatever functions we use to define absolute value need to have this property too. What are some functions, though, that always give positive outputs? Something that comes to mind is x squared. By taking a look at its graph, we can easily see that for all values of x squared is positive. However, the problem with x squared is literally that it squares the value of x. What we want to do is preserve the magnitude of x. But here's where it gets interesting. What if we take the square root of x squared? Wouldn't that just equal x? Well, it would, except for the fact that the square root function, like x squared and the absolute value function, also has a property of returning only positive values. This is the key insight. While the square and square root normally cancel out, the square root function forces everything to be positive. So, the square root of x doesn't just equal x, it actually equals the absolute value of x. And just like that, we've done it. We found a way to write the absolute value function in a completely differentiable form. Now, let's actually take that derivative. By rewriting the square root as the 1/2 power, we can use the power rule to take the derivative of the square root function, leaving us with 1/2 times x squared to the negative 1/2 power. Next, we use the chain rule. Taking the derivative of the inner function x squared gives us 2x. Multiply them together, and then do some algebra. With that, we get our final answer: x over the absolute value of x. And boom, our non-piecewise approach gives us exactly the same answer as the traditional method. When we plot it, we can see it lines up perfectly with the piecewise function we defined earlier. But wait, there's something interesting here. Our derivative x over the absolute value of x is undefined at x equals 0, just like the conditional version. This tells us something fundamental. The absolute value function genuinely isn't differentiable at x equals 0, no matter how we represent it. The corner of the graph at the origin creates a point where the left and right derivatives don't match. The math is actually pretty elegant here. While we found a way to express the derivative using standard differentiation rules instead of breaking the derivative into cases, we still can't escape the essential nature of the absolute value function. Often, math has these beautiful connections that reveal deeper truths about why certain limitations exist. This technique of rewriting functions to make them differentiable is actually used all throughout mathematics. For example, in statistics, while measuring how spread out data is, we could use the mean absolute deviation, which involves the absolute value of x minus mu, or the mean. But instead, we use standard deviation, which squares the deviations and then takes the square root. It's the exact same trick we just used. Engineers use similar tricks all the time, replacing sharp transitions with smooth approximations because smooth functions are easier to work with computationally. The deeper principle here is that mathematics often rewards us for finding the right representation of a problem. Sometimes, the most natural way to define something isn't the most useful way to work with it. That's why it's so important to understand what mathematical expressions really mean, like breaking down where the chi-squared test statistic comes from to determine whether my dad was cheating at Catan. Check out this video if you want to learn about the chi-squared test and see how that investigation turned out.